All right, my favorite class, we're going to go over some rules of probability for Module 9. It'll be really quick. And don't forget you have your project also to be working on. So what we're talking about here, using the rules of probability, the first thing we're going to talk about are complement rules, okay? Not complement like you look nice, but complement like as in completing a whole. Okay, so the probability of an event A and the complement of A will always add up to 1. So what do we mean by complement? So let's come down here a little bit. Let's look at this. If there is a 75% chance of snow tomorrow, and let's say that that is event A, the probability of A would be 75%. Okay, so if we're adding up to 1, remember 75% written as a decimal is 0.75. That means that the complement, okay, and I've also seen it written as P naught. You could write it as P naught also. But the way this class uses it is the complement of A would be A little c is going to be 0.25 or 25%. Okay, so the probability of something happening and the probability of well, not the probability of it not happening, but the probability of its complement, it might not just be that it's not happening, in this case it is, are going to add up to be 1. So that is what we were just talking about up at the top. The probability of A plus the probability of the complement of A is equal to 1. Okay, so what that means is if you subtract, so the probability of A would be 1 minus the probability of the complement. So if we were trying to figure out the percent chance that of snow tomorrow, it would be 1 minus the complement, which was 0.25, which is equal to 0.75, and then below it, the probability of the complement would be 1, or in this case, a probability that it will not snow would be 1 minus the probability that it will snow, or 0.25. Okay. It says down here, make a note that an event and its complement are always mutually exclusive. That means one can happen in the, or that the two cannot happen at the same time. Okay, would be a better way to put it. Now we're talking about the union of two events, disjoint and non-disjoint. So we just talked about things being mutually exclusive, which is the same as being disjoint, which means they cannot happen at the same time. So if we look at this first Venn diagram, A and B are completely separate circles. That means whatever is in A, this heart, can absolutely not be in B. And whatever is in B, let's say this rectangle, can absolutely not be in A. Okay, if they are not disjoint, that means that, say, both of them could have a heart in them. It could be in both A and B. You would only put it in once. All right, let's go over an example. A couple is planning to have 3 children. And remember what I told you maybe a few videos ago about how this book uses gender a lot of times as a binary with just males and females or boys and girls. This is one of those times that we're going to be looking at having a child, but just a boy or just a girl, even though we know that that is not always the case. That is what we are going to be using here for this example. Okay, so they're having 3 children. The sample space S of all the outcomes is they could have boy, boy, boy. They could have boy, boy, girl, boy, girl, boy, girl, boy, boy. You get it. So this is every option that they could possibly have. Okay, you may, I'm going to quickly draw it like this because sometimes when I'm going over something, it makes more sense to me to draw it as a tree diagram. Okay, a lot of times I'll do this. I know the first child could be either a boy or a girl. If you have a boy, the second child could also be a boy or a girl. And then the last child could also be a boy or a girl. When I do it this way as a tree diagram, I know, why am I always putting boy first? Let's do this one. Girl, boy. I know that I'm not going to miss anything with the tree diagram, whereas if I draw it using curly brackets, oops, I forgot something on this one. This could be a boy, this could be a girl. Here we have girl, boy, girl, boy. Okay, so when I draw it this way, I know I'm not going to miss anything. So the first arrow there, that's the first child. This would be the second child. And then this last set would be the third child. If you draw it as a T diagram, if you draw it as a tree diagram, let's look at something here. You're going to have each of these things. You're still going to have a sample space of 1, 2, 3, 4, 5, 6, 7, 8. Okay, but in this case, you're going to count up here. 1, 2, 3, 4, 5, 6, 7, 8. So there's your final sample space. And then if you look at it, the first one's boy, boy, boy. Here, boy, boy, boy. You see that in the tree diagram as boy, boy, boy. Boy, boy, girl is going to be boy, boy, girl. Okay, so you can see them here. Girl, 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 which is the last one that they have here, is going to be girl, girl, girl. So whichever way you are more comfortable with, the tree diagram definitely takes up more space and it's harder to do on the computer. But again, if I have something with just a small amount of outcomes like these 8 outcomes, I'll usually do a tree diagram just to make sure I'm getting everything and not missing anything. Okay, so let's look at these following events. Event A, the middle child is a girl. Okay, let's see. Let's erase some of this so I can go back. 3 through. Okay, the middle child is a girl. How many times does that happen? Let's take a look. Here, boy, girl, boy. Here, girl, girl, boy. Boy, girl, girl, and girl, girl, girl. Okay, event B, actually, let's make this, oh no, that made it green. Let's match these up here. So event A is blue. Okay, and then let's do event B as green. Okay, event B is green. The 3 children are of the same gender. So where does that happen? That happens here. I'm going to do it above, and you'll see why in just a second. 3 children are the same gender only happens twice. You're either going to have 3 boys, or over here you could have 3 girls. So event B is in green. So the question is, are events A and B disjoint or not? Disjoint, again, means mutually exclusive, which means they would never overlap. Well, they are not disjoint because obviously we drew green and blue could both be girl, girl, girl. So let's go down and write it in our table. And heads up, this will be on exam 2, and it will also be on the final exam. Actually, I said exam 2. I know 100% it's on the final exam, and I am approximately 85% it's on exam 2. I just haven't looked at it recently. So event A, the possible outcomes were B, G, B. This is what I highlighted in blue. G, G, B, or, oh, there was 4 outcomes. B, G, G, and finally all girls here. Event B was the green, so that would have been either just boy, 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 or girl, girl, girl. Okay, So let's go through this table. What's the probability of event A? Well, there's 4 possible outcomes. The total sample space was 8, so the probability was 50%, or 1 out of 2, right? Event B, the probability was 2 out of 8, or 1/4, which is 25%. So the final thing it just wants to know is that they are not disjoint. Okay, let's do event C and event D. So let's make event C yellow. Exactly, one of the 3 children is a girl. That is, let's erase so we can start over. Exactly, 1 is a girl. Here, here, here. That's it. And event D, exactly 1 of the 3 children is a boy. Only 1 is a boy. That happens here, here, and here. These do not overlap at all, so they are in fact disjoint. Okay, let's go ahead and fill all of these out. Well, event C, let's just put yellow. I don't want to draw that again. And event D, let's call that pink. Both of them are 3 out of 8. So both of them are less than 1/2. I want to say 3/8 is about 36%, but let's use a calculator. 3 divided by 8, enter, times 100%, 37.5. They are both the same. Okay. So union rules. The union of 2 events A and B, okay, the union, whoops, I thought I was in highlight mode. The union of 2 events A and B is the event representing all of the outcomes that belong to A or B or both. Okay, the union of A and B is denoted as A union B. So it can be either A, or it can be either B, or it can be in both. So in any one of those circles on the Venn diagram. Okay, and it gives us some formulas. If A and B are disjoint, okay, be careful here, we're only talking about disjoint. Mod 10 is where we start talking about not independent events. Then the formula is the probability of A plus the probability of B. We're only talking about, if we have our Venn diagram, okay, and we want A or B, this formula we're talking about is disjoint, which means the numbers you have here, 1, 2, 3, 4, 5, and the numbers you have here, 6, 7, 8, 9, we just add them together. Okay, we would just add not those numbers, I'm sorry, we would add the probabilities of getting those numbers together. There is nothing in the middle because these are disjoint. Following down here, if they are not disjoint, it's going to be a little bit different than that, okay? And here. There's another, see it says, you do this still, but remember this is talking about, let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So both of the circles have 5 in them, okay? So you want to add these up, but what we have to do is we have to subtract how many are in the middle, or else it would get counted twice. You would count it once for A and once for B, right? So you have to subtract it one time, and that's where that minus P of A and B comes into play. That is like if you are talking about choosing cards, okay? And let's say, oh, I'm making this up, so I hope that this example I'm gonna spout off works. But let's say we wanna know what is the probability of pulling a heart, okay, or a king, okay? What's the probability of pulling a heart or a king? And then so we have our Venn diagram, right? And so one circle would be hearts and one circle would be kings. So on the king side, there would be 4 cards, right? You would have one of each of the, I don't want to do this. You would have a diamond king. You would have a clover. Oh gosh, I don't know what this looks like. King and a spade king and a heart king. But I'm going to put heart in the middle because that is both a heart and a king, obviously. On the other side, the number of heart cards is going to be 13. So you're going to have an ace, a 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and the king, which is actually the king of hearts, which is in the middle, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So there are 13 hearts out of a deck of 52. So the probability of pulling a heart is going to be 13 out of 52. And we want to add that to the probability of pulling a king, which would be 4 out of 52, okay? But remember, we are counting that king of hearts right now 2 times. We are counting it here and we are counting it here. So we have to subtract 1 out of 52. We have to subtract one of them because we're counting it twice, but there's really only one card, right? So the probability is actually 13, 14, 15, 16, 17 minus 1. The probability is actually just 16 out of 52, out of 52 that you would pull either a heart or a king. Because there's one which, let's see if I can reduce this, which is really 8 out of 26. Is that half of 52? Which is really 4 out of, what's half of 26? 13? 13, and from there you could do the math, whatever percent that is. 4 divided by 13. Four divided by 13. Approximately 30.8%. Okay. All right, what's next? The intersection of 2 events. So what we were talking about is the union. So we wanted everything. The intersection of 2 events, they only want the cards that are going to be in the middle. Okay, so the intersection of the example that we just did would have been that 1 out of 52, just that one card in the middle. The intersection of two events A and B is the event representing all the outcomes that belong to both A and B. There it is again. And we use this symbol. Before, for the or, we were using the upside down U. I don't know the actual word for that. Did it tell us the actual word for that? It says, what is this? Oh, what is the and symbol? Nope, we're getting to that. Well, I'll look that up and get back to you. Okay. Independent event. The occurrence of one event will not change or affect the likelihood of another event occurring. Dependent event. The occurrence of one event will change or affect the likelihood of another event occurring. So it gives us some examples. Let's go through these. The chance of getting the next answer correct based on whether the previous answer was correct on a multiple choice exam. Well, I mean, honestly, this depends on if they are questions that are based on other questions before. If they were not, then they would be independent. So this one actually I can see going either way. If you guys can know the difference between what I'm talking about here. B, the chance of getting a head on the next flip of a coin if you just got a hit. It doesn't matter. Those are independent. It doesn't matter if you got a head last time. You could get either a head or a tail this time. The chance of passing an exam based on how much have you studied. Well, I think those are very dependent, if you ask me. And D, the chance of winning your next game based on whether you just won or lost the current game. Well, I can see, I'm going to say independent, but I could actually see that being dependent just based on how much you learned out of that. So I guess it depends on the game. If it's completely a game of chance, independent. If it's based on maybe something you had done a game before, it might not be. But let's just go with independent. We're talking about just like straight up games of chance. Okay. So the intersection rule of A and B. So this is where you guys, I'm sorry, I might have said it before. We're only going to do the intersection rule of independent events, and then like it says down here in module 10, we'll talk about dependent events. If two events are independent, then the probability, you just multiply those numbers together. In fact, you can use this formula in any sequence of independent events. So the probability of flipping a coin and getting heads is 1/2, right? The probability of doing again is also 1/2. Okay, so the probability of flipping a coin twice and both times getting heads is 1/4, because you multiply those together. And that makes sense, because remember our sample space would be either head heads, head tails, tails heads, or tails tails, right? And only one out of those four sample space, out of four sample space of 4, only one is actually heads and heads. So that matches what our rule says. And I'm not going to do this last page because I think this was specifically for one teacher that created these notes. And I don't think that we did that. All right. So please make sure you write down any questions you would like to ask me in our next class. And I will, whoops, whatever that was, talk to you guys soon.